Hello everyone, welcome back. Imagine managing multiple conversations at once, all vying for your attention. Sounds chaotic, right? Well, that's essentially what our communication systems are dealing with every second. And the secret to their success? Multiplexing. Now you might be wondering, what exactly is multiplexing? In its simplest form, multiplexing is a technique used to send multiple signals or streams of information over a single communication channel. It's like a highway for data, where each car represents a different signal, all sharing the same road, but without interference. Where does multiplexing come into play? Well, think about your daily life. You're constantly online, streaming videos, making calls, sending texts, and so much more. These activities require a vast amount of data to be transmitted simultaneously. Without multiplexing, our networks would be in a constant state of traffic jam. So the next time you stream your favorite show while video calling a friend, remember, it's all thanks to multiplexing. First up in our exploration of multiplexing types is frequency division multiplexing, or FDM. Now imagine a highway. FDM works in a similar way by dividing the total bandwidth or highway into multiple independent lanes or frequency bands. Each of these lanes is used for a separate channel, allowing multiple signals to travel simultaneously without interfering with each other. This ensures efficient use of the available bandwidth. In practical terms, think of how radio and television broadcasting operate. Each station is assigned a specific frequency band, or lane, within the total spectrum. This allows multiple stations to broadcast at the same time without overlapping or causing interference. Also, consider your Wi-Fi. It also uses FDM to separate users onto different frequency bands, ensuring a smooth internet experience even when multiple devices are connected. So, when you tune into your favorite radio station, you're experiencing FDM in action. Next on our list is time division multiplexing, or TDM. Imagine a roundtable conference where everyone gets their dedicated time slot to voice out their thoughts. That's how TDM works. It divides time into slots and assigns each slot to a different channel, ensuring a fair and orderly transfer of information. The beauty of TDM lies in its simplicity and efficiency. By giving each channel its moment in the spotlight, it ensures that all the data gets through without any channel dominating the conversation. Now let's talk about where we see TDM in action. You may not realize it, but TDM is all around us. It's there when you make a call on your digital telephone, ensuring your voice is heard clearly at the other end. It's there during video conferencing, managing multiple streams of audio and video data simultaneously. In essence, TDM is like a well-organized meeting where everyone gets a turn to speak. Last but not least, we have code division multiplexing, or CDM. Now, if multiplexing is about sharing a single communication channel, then CDM is the party planner. Instead of juggling time or frequency, CDM uses a unique code for each channel to allow simultaneous transmission. Imagine a room full of people speaking different languages. Everyone is talking at once, but you can still have a conversation in your language because the other languages sound like background noise. CDM is a key player in the world of mobile telephony and GPS. With every call you make or text you send, your phone is using a specific code to communicate with the network. It's like having a secret handshake with the cell tower. And in the world of GPS, each satellite transmits its data with a unique code, allowing your GPS receiver to distinguish between signals. So when you make a call on your mobile phone, you're using CDM. Now that we've explored the three main types of multiplexing, let's see how they stack up against each other. First, we have frequency division multiplexing, or FDM. This method divides the total bandwidth available into a series of non-overlapping frequency subbands, each used for one communication channel. It's like having your very own lane on a highway where you can drive without worrying about other cars. The strength of FDM lies in its simplicity and its ability to handle high bandwidth rates. However, it's not perfect. Its main setback is that it requires a guard band between channels to prevent overlap, which can lead to inefficient use of space. Next, let's talk about time division multiplexing, TDM. This method divides time into several recurring time slots of fixed length, one for each subchannel. It's akin to having a round-robin dinner, where each dish gets its turn at the table. TDM shines in environments where the input data rate of the senders is lower than the output data rate of the receiver. However, its weakness lies in the fact that if a user has no data to send, the time slot is still allocated and remains unused, leading to potential inefficiency. Finally, we have code division multiplexing, or CDM. This method assigns a code to each data channel to differentiate it from others. It's like having a secret handshake for each of your friends. CDM's strength is that it can accommodate a large number of high-speed users with minimal interference. However, its weakness is that it requires complex encoding and decoding systems, which can be expensive and difficult to implement. So, to summarize, FDM is like having your own lane on a highway, TDM is like a round-robin dinner, and CDM is akin to using a secret handshake. Each has its strengths and weaknesses, and the choice between them depends on the specific requirements of the communication system at hand. So there you have it, the world of multiplexing in a nutshell. A fascinating mix of technology and organization that keeps our world connected. As we look towards the future, the role of multiplexing in communication systems will only continue to grow. The potential applications are limitless as our world becomes more connected and data-heavy. We can expect advancements in multiplexing technologies to accommodate the increasing demands for high-speed, high-capacity communications. Imagine the possibilities. Quantum multiplexing could revolutionize how we transmit and process information, moving us far beyond the limitations of current digital systems. Meanwhile, optical time division multiplexing may hold the key to ultra-high-speed broadband networks, capable of handling the data traffic of tomorrow. There's also the potential for multiplexing to play a significant role in the development of smart cities, where vast amounts of data need to be transmitted and processed in real time. With the rise of the Internet of Things, the need for efficient multiplexing is more crucial than ever. And with that, we conclude our journey through multiplexing. Until next time, keep exploring, keep learning, and remember, communication is key. Thanks for watching, and please subscribe.